talking today about infrared emission lines in the dusty interstellar medium. So.
All right, thank you for the kind introduction. Yeah, I'm Elijah. If you haven't met me, I'm a fourth year. I'm in the observational cosmology group, and I do like superconducting detectors to detect infrared radiation and do like astronomy. But this talk is going to be more about kind of the science behind why we care about emission and infrared specifically, and like what we can learn from it, and why dust ties into that specifically. So the outline is kind of mostly like a review of some theory and observation papers from the 80s, and the reason I'm rehashing all these old papers is because there's a lot of stuff I reviewed for candidacy, so it's kind of like on the brain currently. So the format is going to be, first off, like what is dust and why do we care? Because I guess if you just hear the word dust, it doesn't sound too interesting, but it ends up being pretty important for, because a lot of astrophysical processes, like in this talk specifically, we're going to talk a lot about star formation, tend to be happening in dust obscured regions, and so if you want to understand what's going on in there, you have to know about the composition of the dust that's obscuring the process you're trying to study. Next, I'm going to move on to infrared emission lines. Why do we see them in these dusty regions? So these lines are essentially like fine structure lines of atoms that get excited by scattering off of warm dust. So this is a quantum scattering problem. You have to do some kind of gross looking quantum mechanics to get these collisional excitation rates and understand at what rate you're actually exciting these lines, and as a result, how much luminosity you're going to see from them. And also, finally, we're going to get to what can we actually learn by observing them. So we're going to look at two examples. The first one is an extragalactic source that's actively forming a lot of stars, and then it's going to be a molecular cloud in our own galaxy. Okay, so first off, what is dust? It's kind of a catch-all term for solid particles of heavy elements, so oxygen, carbon, silicon, magnesium, iron, etc. Just heavy elements with sizes that are some fraction of a micron in interstellar medium. And they make up in total about 1% of the ISM mass. So as you can see in this picture, this is an image, a multi-wavelength image of a molecular cloud in our own galaxy, molecular gas and dust cloud. So what's happening here is that you have a bunch of stars emitting in this top left in the visible, and these small dust grains appear dark because it's essentially scattering and absorbing the starlight coming from behind the cloud, and you just see a black blob instead of the stars that are hiding behind it. But as you go to longer wavelengths, as you enter the near infrared, so going from top left to right, and then bottom right to left, you begin to be able to see through the cloud, and this because directly because of the small grain sizes of the cloud. Essentially, they act as like little antennas, and when the wavelength of light gets larger than the size of the antenna, quote unquote, then it's no longer efficiently able to absorb the radiation. So the dust is just transparent in the infrared. Okay, dust plays a pretty major role in regulating the temperature, like the thermal balance of star forming regions, because as I said, the star formation often happens in these dusty obscure regions because you have this like molecular cloud with a bunch of gas and also some fraction of dust, and the dust absorbs a lot of ultraviolet radiation. What happens is that the dust gets electrons knocked off it by this energetic UV radiation, and the electrons bounce around inside the gas and dust and heat it up. Essentially, just the kinetic energy of the ejected electrons just thermalizes, and the gas and dust heat up. And we call this photoelectric heating. In addition, you have these non-dust, just isolated atoms, so like carbon, oxygen, nitrogen. These can also be photoionized because you have this energetic UV flux happening. And then the way this gas and dust cools itself after heating up is the dust just radiates like a gray body, not a black body because it doesn't have perfect emissivity, so we call it a gray body, and that's just thermal emission, broadband infrared. And then the ISM gas, as we're going to get to, you have these fine structure emission lines which can get excited. These are thin, like spiky features in the infrared that can then radiate, and actually it turns out that throughout most of the cloud, so this x-axis is a graph of visual extinction, so it's essentially just a measure of like how far you get away from the stars and how deep you go into this dark cloud. Throughout the cloud, these emission lines are pretty important for cooling the gas and dust, or the gas particularly. And then looking at the distributed emission from a full galaxy, so this is kind of like more or less like an integral over a lot of these different star forming regions. You see that you have this blue bump here. This is just the raw like ultraviolet visible radiation from the stars, and this big hash chunk gets taken out of it because you have all this dust that's surrounding it, and then it's just a big bite that gets taken out of the ultraviolet part of the spectrum essentially, and it just gets moved over to this red bump here, which the shape of it is determined by that gray body curve I was talking about, where it's just the dust radiating thermally, and then on top of it, the gas pokes above the thermal emission with these like spiky fine structure lines, which we're going to get to. And I should also mention this is it's an example of an actively star-forming galaxy, or a typical lake-type galaxy, which has, it's a spiral structure and it has more gas and it's actively forming stars. Okay, so the fine structure line that I'm going to concentrate on a lot in this talk is the 158 micron line of ionized carbon, and I'm just going to refer to it as C2. That's usually what people call it. The reason this comes up is because in carbon you have, ionized carbon in particular, you have one free electron, and it's sitting in the 2p state here, and if you don't do any perturbations, then it can have two angular momentum states, so you add the angular momentum of the orbital part, so that's L equals 1, plus the spin part, so you can get either J equals 1/2 or J equals 3/2. These are degenerates, they have the same energy until you add spin orbit coupling corrections and relativistic corrections, which cause this level to split. Then you get an energy that corresponds to a wavelength of 158 microns or 92 Kelvin. So these numbers I'm kind of going to use interchangeably throughout the talk. And the pretty much like only way this line is excited in these dusty regions is through collisional excitation off of the warm gas, because the next highest energy, so the only other way you can really excite that level, since it's a forbidden transition, is to excite to the n equals 3 state, and then have it cascade down to the n equals 2, j equals 3/2 state. But since the n equals 3 state is so much higher in energy, that's not really going to happen, so mostly this just gets excited by bouncing off of hot gas, which is mostly hydrogen. And so you have C plus in the ground state, it hits the hydrogen atom, and then it comes out of the scattering with the hydrogen still in the ground state because the energies are not large enough to excite it, but you have enough energy to just excite this like lower energy fine structure transition in the ionized carbon. And then this is kind of just a graph of what the interatomic potentials look like. So you have, I guess my chemistry knowledge is kind of rusty, but essentially you end up with like an attractive potential representing the electron being in the binding region between the two atoms, and that's like this kind of Leonard-Jones like R6 plus, or 1 over R6 minus 1 over R12, I think I got that right, potential. And you have this antibonding potential, which is when the electron's in sort of this antibonding region. So you have to consider both these potentials when you're solving the quantum scattering problem. Okay, so getting to the mathy part of the talk, we're going to do essentially a quantum scattering problem. So we have to understand what's the interaction energy between these two atoms when they're colliding, and it's made up of 4 terms. So as we just said, we have the relative potential energy of the atoms A and B, which we're going to take to be ionized carbon and hydrogen, just atomic hydrogen. That's like this bonding term and this anti-bonding term. Then you have the internal Hamiltonians, which are basically just like the internal states of the atom. So HA would include like the fine structure transitions of the carbon atom, and then HB would include all the electronic energy states, the hydrogen atom, which we're not really going to consider. We're not going to consider most of them because they don't really get excited in this collision. And finally, you have just the relative kinetic energy on the left. So this is just the time-independent Schrödinger equation. Since this Hamiltonian on the left is fully invariant with respect to spatial rotations, that means the eigenstates should be also simultaneous eigenstates of the angular momentum, the total angular momentum. So you get this separable sort of solution where you have a radial part, which is the part we're going to care about solving for. That's this f function. And then you have this angular part, which is some huge mess of like spherical harmonics, which we're just going to ignore because we don't really need to. I didn't want to type all that out, to be honest. But yeah, and then this gamma just refers to the internal states of the atoms basically, and their relative angular momentum. So JA and JB are the internal angular momentum of A and B, and we're really going to care about just the internal angular momentum of the carbon atom, because that's what drives this fine structure transition. And also this L is relevant because you're going to see it comes up in the when we kind of like plug in this on-slot solution into the Hamiltonian, this L also plays a role. Oh yeah, and also this is inelastic scattering. It's a bit more complicated, I guess, than like if you did quantum scattering in Griffiths, because you can excite like a higher energy state in the ionized carbon when it comes out, so it's emerging with a higher internal energy. Okay, more math. Basically, we just apply the kinetic energy operator, which is just a bunch of derivatives to this each term in this on-slot solution, and just grind through the derivatives. It actually simplifies a lot, just because this right term is only radial derivative, so it just acts on the radial part of the function. And then the left part is just the angular momentum operator, total angular momentum operator times some constants, or times r, and constants. So it's just going to act on the angular part and give you the eigenvalue of the relative angular momentum of the two states, which is L. So you get L times L plus 1, so that becomes much simpler. And then also, applying the individual Hamiltonians is pretty simple, because the wave function is also in an eigenstate. So the individual atoms before colliding are also in like their own individual eigenstates. So they have some energy, like EA for atom A and EB for atom B. And that's alpha and beta here just to note like which, it's a quantum number essentially for like which state the atom's in. Putting all together, I think this is roughly where the math starts ending. Yeah.
You're going to be sure and do this for your candidacy exam, right? Take line by line on all this math.
I'm trying to not have this much math in my actual candidacy talk. We'll see.
Because they'll be like, oh, I think you missed it, negative.
Maybe if I want to put him to sleep, I could try that. But I don't think that should be the strat.
So if your talk is dragging, make sure to do that.
Yeah. Okay, so this is just plugging in the math we did in the last couple slides into the sum. So you're summing over all these like internal quantum numbers, the angular momenta, and you use the property of the spherical harmonics that they're orthonormal. So you just multiply it by gamma prime, and integrate over all the angular coordinates, which will select out just like one gamma coordinate on the left-hand side of this equation. The right-hand side of the equation is not so simple, because you also have this potential term, which kind of breaks that orthonormality. So you have like this kind of matrix element, more or less, of like the potential. What you end up with is this kind. So on the left-hand side, this is like I guess Bessel's equation, which you have solutions for, and then you have this potential term, which is the sum of these potential matrix elements on the right-hand side. So it's a coupled set of differential equations, which is kind of gross, but in practice what you do is you truncate the set of states that you solve for by a lot, because a lot of them aren't actually going to be excited. For example, the hydrogen states, you don't really have to care about the excited states. So it becomes quite a bit more simple when you don't consider the full set of basis functions. Okay, yeah, and it becomes even simpler if you just ignore the potential altogether, which is what happens when you go far away. And that's actually what you care about the most, because when you scatter, the particles are just interacting for a little bit and they fly out to infinity. And essentially what you're going to do is like solve. So this is, I guess, similar to what you do in Griffiths, just a bit more generalized, where you solve the equation when you're away from the potential, and you get these sum of Bessel functions with some coefficients a and b, which also depend on your internal quantum numbers. And then you compare that to your solution that you get from the full general equation, and you just apply the boundary conditions to solve for these coefficients. And then there's like a more general version of this cross-section formula that applies to inelastic scattering that you use to actually calculate the scattering cross-sections once you get these a and b coefficients. Okay, so after you do all that, I think that's probably the hardest part. Then once you have the scattering cross-section as a function of the kinetic energy, you have to like apply it to an actual physical case, which is you're in this thermally equilibrated gas, and so the kinetic energies will follow a Maxwellian distribution. And so what you have to do to get the average cross-section is just average over that distribution of kinetic energies. And we're applying this specifically to the cross-section where you're starting in the ground state, and after scattering, you're exciting the C2 line. So you're going from j equals 1/2 to j equals 3/2. Okay, and once you know the scattering cross-section, you can convert that to a rate by just considering, like, if you have an incident C+ ion and it's moving through a gas of hydrogen atoms, then what's the probability of scattering per unit time? So it's just the probability of scattering per unit distance times the velocity, dz dt, and that just ends up being the density of scattering sites, which is, we're calling n here. This is the density of hydrogen atoms times the cross-section for scattering times the average thermal velocity. And then we define this quantity called the collisional excitation rate, which is just that scattering probability divided by the density. So the way this maps to an actual like rate of scattering events is that you just multiply by the densities of the two scattering partners, and you get a rate of collisional excitations per density or per volume per time. Okay, the good thing is that once you have the excitation rate, you actually get the de-excitation rate for free pretty much, because the interaction is mediated by the electromagnetic force, and so that Maxwell's equations obey time reversal symmetry, which just means like if you just have these two equations and you're considering their balance in thermal equilibrium, they have to balance each other exactly, specifically just the two collisional excitation and de-excitation rates. So that gives you this equation here, where you have excitation times density of excited state atoms, or sorry, this is, did I get this right? I think I got that wrong. Yeah, this is supposed to be gamma 21 N1, so it would be excitation rate times ground state density times hydrogen density, and then that equals de-excitation rate times, that would be N2, so that should be excited state time density times hydrogen density.
Sorry if I missed it before, but so what is the lifetime of that, of those?
Yeah.
States? So the de-excitation is like, you can say it's dominated by collision.
I think that's going to be in the next slide, because there's two processes you can de-excite with, so we're going to add in spontaneous emission after this, but this is just kind of to, it's a nice trick to get the de-excitation rate, just based on like detailed balance. So I hope...
When Elijah introduces the Einsteinian coefficient, is 1 over that.
Yeah.
Oh.
That is the time scale.
I hope the rest of my equations, the indices are correct. I'm just going to pretend they are, because this is wrong, but I think everything else is right. So yeah, since it's in thermal equilibrium, you just have the Boltzmann factor governing the ratio of the densities of atoms in each state. So you have just the degeneracy of excited state times the energy, the exponential factor, and then same for the ground state. And using these two equations, you just get this expression which gives you the collisional de-excitation rate at some temperature. Okay, and then the next step is to add spontaneous emission. We're not going to add the other Einstein coefficients because generally, I guess you could just take my word for it, the C2 line is generally optically thin, and that means that the photons, as they pass through the gas on their way out, they're not really going to trigger too much absorption or stimulated emission, so you don't include the Einstein B coefficients in this equation. But you can just solve this equation for the ratio, the population ratio, using the collision, excitation, and de-excitation rates, and you get basically that it's the Boltzmann factor, so you get this Boltzmann ratio on top, and then it's divided by 1 plus this like critical density divided by the density of hydrogen. So if the density of hydrogen is much greater than this critical density, they're just going to follow the Boltzmann distribution. If it's a lot less, then the atoms are basically all going to be in the ground state, and they're not going to be collisionally excited often enough to like have a reasonable population sitting in the excited state. Essentially just because the radiative spontaneous emission is happening faster than you can collide it up to the excited state, so they all just sit in the ground state. Finally we're getting to the actual observables that you can get from these lines. So the line intensity is the photon energy. So it's going to be a measure of basically energy per time, and then per A omega product, which is just per area per steradian. So you have the photon energy, you have 1 over 4 pi, just giving you the per steradian part. Spontaneous decay rate, that's the Einstein A coefficient, so it's number of probability of decaying per unit time. And then the last two terms here are just the density of, the number of C plus atoms per area. So that's the column density. And then you have the fraction which are in the excited state. and then you use conservation of total particle number, so you have a total number of C plus atoms, which is just the ground state plus the excited state, and you use the ratio that we derived earlier, and you have this expression that tells you, based on what's the density of colliding partners and the temperature of the gas, how many particles end up being in the excited state as a fraction of the total density. Okay, we've kind of been assuming that the lines are optically thin, but just to check, we're gonna use this equation from Rybicki and Lightman, which gives you the optical depth, as a function of the amount of absorption and stimulated emission that's happening when a photon travels through the gas. So that's what these two terms are in the parentheses basically. The first one is what's the probability of exciting a ground state atom to the excited state, so it's like a positive term, and then you subtract that because you can also stimulate an excited state atom to emit a photon, and so that's essentially like negative optical depth, more or less, because you're like inducing the gas to emit more photons rather than absorbing it.
So this alpha term is some absorption coefficient?
Yeah. Yeah, so the optical depth will just be this coefficient times the distance. You just integrate over the path. And you also have this like Doppler broadening term, which is just a distribution of line centers, essentially, because when you have like gas moving around, it gets Doppler broadened just due to Doppler shifting, and that's just proportional to the, or it's inversely proportional to the velocity dispersion. So yeah, this equation is kind of gross, I guess. Like, we're not going to really pay too much attention to this because it's going to simplify a lot when we actually end up using it in certain limiting cases. Okay, so getting to an example, this is C2 emission seen in a galaxy, a somewhat nearby galaxy, which is forming stars about 10 times as fast as our own galaxy. And so we mentioned that C2 can come from these kind of like dusty star-forming regions where you ionize a lot of carbon, you also ionize a lot of dust, which heats up the ionized carbon and the gas, and it collisionally excites this line. And then you just get this like big broad emission feature sort of around the nucleus, because as you can see, so this is a full like zoomed out picture of the galaxy, and these circles are the beams within which this C2 line was observed, and so they're pretty big compared to the size of the galaxy even, which means that you're going to get a lot of like line broadening. It's not a thin line because there's a lot of gas moving around in different directions, so you get this huge kind of like broadened velocity profile. But we can see it's mostly, the strongest emission is at the nucleus, which tells us there's a lot of stars forming there. And also just the fact that we see strong C2 emission at all kind of tells us a few things. The first is that the fact that a lot of atoms have to be sitting in the excited state means that the gas has to be warm and dense, right? Because you have to have dense enough gas to like be above the critical density, and you also have to have warm enough gas to actually be exciting this like 92 Kelvin transition. And it also implies high C plus column density, just because to have a high to see a high intensity from this line, you have to have a lot of just, C plus atoms to emit, basically. Okay, so what you measure is actually the line intensity, which we talked about earlier, which is in these units of power per A omega product. But we can pretty easily convert that to luminosity just by considering what's the beam size that we observe the galaxy with. So each of these circles have an effective area of about a square kiloparsec. So that takes care of the area part. You just multiply by A, and then you just multiply by 4 pi to take out the steradians part, and you get a full kind of bolometric, well, not really bolometric, I guess the full power in this line integrated over this line profile ends up just being this I term times 4 pi times the area of the beam, which comes out to about 4.6 times 10 to the 7 solar luminosities. And to put this in perspective, it's about 0.5% of the total infrared luminosity of this galaxy. So just in this one line, there's actually a pretty significant portion of the total galaxy luminosity.
So what was the point of like defining the unit with the steradian in the first place?
It's just because it's what you observe with like a real instrument. So you have, I think you could look at it the other way, where you have like a detector with some area, and the source on the sky is like some solid angle. So what you really observe is like per area per steradian power.
So this would be the luminosity.
It's a surface brightness.
Okay.
Yeah, or I guess I'm calling it intensity. That's what I is, which is like when you do an actual measurement, that's like kind of the result you end up with.
I guess I'm just trying to understand why it's 4 pi or something, or not like the area in the sky, or.
Oh yeah. I guess because we're only seeing like part of the solid angle. Like if you consider the full emission of this nucleus, it's like going out to 4 pi, and we're just seeing some fraction of that.
So this is like not anything to do with the observer. This is like our inference of.
Yeah, this is from the perspective. I guess it's from the perspective of the source. Normally, like I think normally when I think about this, I think about it the other way, where it's from the perspective of the observer, and you have like an area of detector, and you have a solid angle of like observed stuff.
Yeah.
But it's equivalent the other way around too, because just there's some like theorem that the A omega product is conserved whichever direction you look in, so it's equivalent. Okay, and to confirm that we can actually assume this gas is optically thin, we could use this formula from earlier, but with a few simplifications, because like we said, we're assuming that it comes from warm gas, which means the temperature of the gas is much higher than the excitation, or not that's the wrong word, much higher than the transition temperature. So that's just the photon energy divided by Boltzmann constant comes out to 92 Kelvin. And also assuming that the hydrogen density is high enough such that it's much larger than the critical density, because you have to have kind of a critical mass of like, or you have to have a significant fraction of the carbon atoms in its excited state, which means that N has to be a lot bigger than critical density. So when you take those limits, it simplifies a lot. It basically just depends on 3 factors. So it has this prefactor, just numerical factor 0.16, and then the hydrogen density is proportional to that. It's inversely proportional to the velocity dispersion, so just the broadening of this line basically. And it's inversely proportional to the gas temperature. So yeah, we call the region in which this C+ normally exists in the photodissociation region. That's like this kind of interface between the fully ionized gas and the fully molecular gas, and that's where you end up with most of the ionized carbon in these star-forming regions. And kind of hand-wavily enough, like models of these regions suggest that the values that you expect for these parameters give you optically thin emission, and yeah, it's hand-wavy. Okay, so with that, knowing that means we can use, let me think. Okay, so now that it's optically thin, we can use the equations we derived earlier to estimate the column densities of the gases. So again, this equation for the fraction in the excited state is going to simplify a lot, just because T is much greater than 92, N is much greater than N crit, and so you just get this factor, which is essentially like, just depends on the degeneracies of the 2 states.
Do you know the critical density off the top of your head?
It's like 4,000 per centimeter cubed, something like that. I think it depends like weekly on the temperature, but it's like in that ballpark. Yeah, and then the degeneracies are easy to calculate just because it's just like angular momentum state counting, so it's just the number of JZ, what's like the number of magnetic, or yeah, the number of orientation states you have of the angular momentum. So it's just 2J plus 1. So for the ground state, that's just 2 times 1/2 plus 1, which is 2, and then similar for the excited state, it's 4. So you just get this numerical factor, which gives you the ratio of atoms in the excited state. Okay, plugging that into the luminosity equation, so the fraction just comes out to 2/3, and we equate that to the luminosity we measured earlier. And then all you have to know to calculate the C+ column density is just this radiative spontaneous emission coefficient, which I think is calculated from like perturbation theory. I'm not sure like how easy this is to directly measure in the lab, but there's like standard values for it. Yeah, you can calculate a column density for C+ of, so this is more of a lower bound of 9 times 10 to the 17 per centimeter squared, just because the gas is not exactly perfectly optically thin, and if there's some optical thickness, then we're going to underestimate it a bit. And then using a standard value for the abundance of C+ to hydrogen gas, then you can also calculate the density for hydrogen. You can see it kind of squares away well with our earlier assumption of the column density of hydrogen in the photodissociation region. So everything kind of hangs together more or less. Okay, finally, I think this is getting towards the end of the talk. we're going to discuss a little bit of a more complicated example, which is a system with multiple quantum states that can be collisionally excited. In particular, the CO rotational ladder, which is a diatomic molecule, so it's just carbon bonded to oxygen. And the reason we care about this is because essentially a thing that you want to measure a lot of the time is the amount of molecular gas in one of these clouds. So the amount of H2, which is just like in the coolest regions of the cloud far away from the stars. But it's hard to measure direct emission from H2 just because this Einstein A coefficient is essentially determined by the dipole moment of the molecule in question. And since this thing is perfectly symmetric, so it has two hydrogen atoms, there's no dipole moment either way. And so you can't actually drive dipole transitions to this thing. You have to consider the quadrupole transitions, and since those are much less common, it just means that the A coefficient ends up being very small, and you don't see a lot of radiation from this molecule. So instead, the reason CO is used is because the atoms are obviously not the same. So you end up with this dipole moment and a much larger A coefficient. And on top of that, it's the most common molecule after H2, so it's just a good kind of tracer of molecular gas. Luckily, the Hamiltonian here is a lot simpler. It's just the rigid rotor problem, which is just basically the total angular momentum operator. And if you take the differences between the energy states, they're just proportional to the angular momentum. So you just, each frequency is just proportional to, each photon frequency is proportional to L, the rotational angular momentum of the state. Okay, but the difference between this and C2 is that it actually usually ends up being optically thick, especially the lower level transitions, like the first excited state to the ground state. Just because there's so much of it, this factor, which depends on the densities of the CO, ends up being pretty large. So you end up having a large amount of absorption as the CO emission escapes the cloud. Okay, and the consequence of having a high optical thickness is that you emit some kind of starting value of intensity. You can call it I sub nu 0. You go through this cloud which has a large alpha and it's at some temperature. As it traverses this cloud, basically what the intensity is going to do is going to follow this equation here, just the radiative transfer equation. And you could see that, it's going to be stable when the right-hand side is equal to 0 because then your d optical depth is not changing anymore, so it's going to kind of stabilize that value, and that's achieved when I sub nu equals the black body value of this cloud. So if it goes through a large amount of optical depth, it's just going to come out with essentially the black body spectrum of this cloud. And an example of that, so looking at a actively star-forming molecular cloud in our own galaxy, in this 1 to 0 transition, you see not a lot of there's very weak emission from CO over here just because there's like essentially none of it because it's being dissociated by the energetic UV flux. And then as you move through the dust, so that's moving along this purple arrow, you get less and less UV because it's like being gradually absorbed by the dust. And eventually you get such a low amount that CO can actually start recombining and you end up with CO here. But this is also still pretty hot gas here, so you end up with a lot of CO in a very hot region. And so this kind of front here is where you have the largest amount of CO emission. And then as you keep moving along, then you have a lot of CO still, but the gas is less hot, so you're not exciting this transition as much. And these contours here, since as I mentioned it's optically thick, they kind of just end up tracing just the temperature of the gas itself, or rather the temperature of the CO specifically. So the temperature you can see peaks at about like 30, 35, maybe 40 Kelvin, and then decreases as you move away, just because you have less UV flux heating the gas, and then decreases as you move towards the stars as well, because you have just no CO there, because it's all dissociated. That's it. Thanks. I'll take questions.
Any questions?
There's a lot of math, there's a lot of quantum mechanics here. You showed some examples. Where does this tie to your work?
Yeah, so since I mentioned C2 is a tracer of these star-forming regions, if you want to understand sort of like the large-scale emission across the galaxy or across like even sort of cosmic time, you can like map the strength of the C2 line, for example. to just understand like what's the density of star formation happening somewhere. And so whether it be in a galaxy or you can measure like the line if it's redshifted, because the wavelength that you measure it at will be it'll tell you the redshift of the galaxy you're observing it in. You can tell like what's the star formation right there. That's kind of one aspect. And you can sort of do the same thing for the carbon monoxide. It's just that it traces cooler gas instead of hot star forming regions.
Is that going to be one of your projects?
I'd say this talk is sort of like not very closely related to what I actually do. It's just the science justification for all of it. I work in the lab a lot doing detector stuff.
I can ask you questions, like if you want to talk science, I can ask you questions that your candidacy committee might ask you, but that may not be fair.
Well, I asked for it.
Yeah.
So how, at what redshift can you do this before it starts to be complicated by other stuff?
I mean, people are trying to do like C2, like large scale mapping at really high redshifts, like 5 to 9, like reionization. And the reason that's good is because you end up redshifting it so much that you can actually see it from the ground. Like there's transmission windows where in like sub-millimeter radiation actually gets through. So there's a few projects to try and like map large scale structure using C2 emission. And also with CO. CO has the advantage that basically you run into a problem that there's like a degeneracy between what line you're actually observing and like what redshift it's at. But if you like cross correlate different CO wavelengths, you could kind of like get around that problem a bit.
You just mean because the ladder is shifted, kind of.
Yeah, but they always have this ratio relative to each other.
I didn't realize it would be easier.
Yeah.
In some cases, that's cool.
It's also brighter, I think, generally. Like CO, if you're trying to observe high redshift C2, it's going to be a lot dimmer than like local or like cosmic noon, like Z equals 2 CO, just because it's like closer basically, and there's a lot of it.
Any other questions?
Can you go back to the slide where it's the galaxy with the bubbles of different histograms?
Yeah, I think was it the last one? This one?
It was
Or the one
I mean,
before?
the one before.
Like with the this one?
Yeah, that one. Hold on. Go back.
This one?
The
No.
one where I asked the one over 4 pi question, right?
Yes.
Yeah.
This. Yes. This
Okay.
one. I guess. Do we expect to see something like this, and do we use this sort of the M82 distribution of all the histograms as a function of placement of the galactic image as like a test for other galaxies? Or I guess
Like that are behind it, or?
like I guess is this what we would expect to see from a galaxy like this? And then like for other galaxies, is it sort of if we see something different, we're like, oh, something must be up? Or
Yeah, you can learn a lot about like from the distribution of C2 intensity, because it's, again, it kind of like traces dusty star formation. So if you see like somewhere in the galaxy, you know, like, oh, there's a lot of molecular clouds here. Another thing you could do is like look at just the velocity displacement or dispersion of it to understand like, is there gas outflows or something?
yeah.
This measurement is kind of you're not able to do that because the beam size is so big and you're just grabbing so large an area that you can't really learn much. But there's more things you can learn with like smaller beams, I suppose. And then if you're looking at like really far galaxies, then it's a point source and you can't really do the spatial mapping anymore.
I see. Is this like the standard beam size? Or is
These-
there a standard beam size?
These papers are all really old, so I'm sure better measurements have been done since then.
Okay.
So can,
Yeah.
can I ask, like, I'm not sure if this is a fair question or not, but what about star formation is this tracking? Is this like winds off of AGB stars or something? Like,
It's tracking like young star formation because it's tracking like O and B stars, which emit a lot of ultraviolet. So just like starburst activity, because that's typically like what a photodissociation. I always butcher that word. That's what a photodissociation region is. Essentially, is like a lot of stars forming quickly and then like carving out this sort of like dissociation front, and it's kind of I guess like relatively fast timescale process, all things considered.
Oh right, I see. It's not tracking actually like how much stuff there. Like that's
Yeah, it's tracking like young, bright, like blue stars specifically, but like obscured by dust, and which that's the reason infrared matters, because like the dust makes it so you can't observe all the UV directly.
Do you have anyone know what those little histograms are? The thin histograms?
Yeah, that's CO. So they also measured the
Oh.
CO 1-0 transition. I think another point of this paper that I didn't touch on was like showing that they kind of trace each other. Like you see CO where you see C2, and that's because like if you have these molecular clouds, part of it is like this molecular region, and you have CO there, and then the part closer to the stars has like the C2 emission, but they're kind of like in the same regions roughly.
What does the resolution mean?
Yeah,
The 5.
yeah, that's I guess just like essentially the wavelength resolution of the instrument they use to do the spectroscopy.
Okay.
So you have like these bins, I guess, is like where you placed your center frequency, but then you have some uncertainty just due to like the instrumental uncertainty.
Cool. Any other questions? We can thank our speaker again.
All right, thank you.